All right, class, settle down, settle down. Everybody take their seats. Thank you. So, let's do some uniform circular motion problems. If you have your notes handy, that's great. If you don't, then I'm just going to sort of recap some of the things that we need to know. So the speed of something moving around a circle at a constant speed is distance over time. That's the distance for one lap, and that's the time for one lap, circumference over period. And the centripetal acceleration of something in uniform circular motion is omega squared r. That omega, that is the angular velocity. And you could alternatively use v squared over r. Same deal. And I think that's the most of what we need to know. Some other basic things about circles, perhaps. We do need to know that this centripetal acceleration is always opposite to the direction of the displacement, the position vector. Or in other words, it's centripetal toward the center. That'll do. All right, so carnival merry-go-round. The merry-go-round, I don't know about you. I always get merry-go-rounds and Ferris wheels mixed up. I don't usually get them mixed up if somebody says the two things in the same sentence. But when somebody says just merry-go-round, sometimes I think of a Ferris wheel. So a merry-go-round, in case you didn't know, is the one with the horses that go up and down. So that rotates around a vertical axis at a constant rate. Man standing on the edge has a constant speed of 3.66 meters per second. How do you know, you might ask, whether this is the v or the omega? Well, this is in meters per second. If you're talking about an omega, that's radians per second. And a centripetal acceleration of magnitude 1.83. All right, the position vector locates him relative to the rotation axis. That just means that we can imagine that like the center of the merry-go-round is at the origin. That's all that means. And just makes it easier for us if we imagine it that way. What is the magnitude of r? Okay, so let's see. I guess I got my centripetal acceleration is equal to v squared over r. I call that AC there. So that means that r is equal to v squared over a, which is that, which gives me an answer of right, 7.32 meters. Is that part A of this, or yes, that is part A. Part B. What is the direction of r when A is directed due east? Well, r and A, the position, if the position is coming from origin and the acceleration, are always going to be opposite to each other. So for part B, when the acceleration is pointing east, the position will be going west, since they're opposite. And when the acceleration is pointing south, the position will be pointing north. And that's it. All right. 59. Woman rides a carnival Ferris wheel. There you go. That's the big one where you're sitting in a little bench kind of thing, and you go up and down in a big circle, like this, with the little seats hanging there and so on. Oh, that is just a great Ferris wheel right there. Like the London Eye is a Ferris wheel, for example. All right. It has a radius of 15 meters. Completes 5 turns about its horizontal axis every minute. 5 turns per minute. And the first question is, what's the period? So that has something to do with this, obviously. Well, period is equal to how many turns there are how much time it takes for one turn or rotation. So I basically have that here. I have a time here, 1 minute, and then I have here 5 turns. So I just need to like reduce this or divide that out. So that's the same as 60 seconds per rotation, per 5 rotations, which is 12 seconds per rotation. So that is the period, 12 seconds, because the period is the amount of time for one rotation. So 12 seconds. B, what are the magnitude and direction of the acceleration at her highest point? So let's see. What do we have? I've got, that's what I'm looking for. Now I have right here the period and the radius. So I'm looking at this, thinking that first, maybe I'm not going to do that first. I need to find this, 2 pi r for t. So let's do that. So that's 7.85 meters per second. And then her centripetal acceleration will be, I guess I could have done, we could have also, I'll back up in a second. So I found the V and did this. That would be the magnitude of it right there. The part C, they want the direction. So when she is up at, where is she? At the maximum, at the highest point. So the direction of that would be down. Don't say south because that doesn't make sense. It's straight down, not south. D, what are the magnitude and direction of her acceleration at the lowest point? So for part D, well, it's uniform circular motion, so the magnitude of this does not change. And when she's at the lowest point, the direction will be up. So there you go. So what I was going to say back here is, instead of finding the V, I could have used this and found the omega. Because if you look back at your notes, we know that, remember these, your notes. I don't put a box around this, but there it is. Omega is 2 pi over the time period of that period. So I could have done here, omega is equal to 2 pi 12 seconds. And then I could have used that to find the centripetal acceleration. It gets you the same answer. 61. When a large star becomes a supernova, its core may be compressed so tightly that it becomes a neutron star with a radius of about 20 kilometers. If a neutron star rotates once every second, yikes. What is the speed of a particle on the star's equator? Okay, so it has a radius of 20 kilometers, which is 2 times 10 to the 4th meters. And it rotates once per second, so the period is 1 second. So let's do this. I'll do this one like so. So that means its angular speed is 2 pi radians every 1 second. I don't know why I wrote another equal sign there, because that's all good. I don't need to do anything else with that. So for part A, again, what's the speed of a particle on the star's equator? Well, I guess for the speed, we're going to do 2 pi r over t, so that's 2 pi times 2 times 10 to the 4th meters over the time period. So that makes sense. That's just 2 pi r, right? If it's going around once a second, then the speed is going to be the circumference every second. So 2 pi times 20k is about 1.26 times 10 to the 5th meters per second. That's fast, in case you were wondering. That's part A. Part B, what's the magnitude of the particle's centripetal acceleration? So now that I have this, I can either do this squared over r, or I can do this omega squared times r, either way. It does not matter. Let's do this way this time for fun. So that's 2 pi squared times 2 times 10 to the 4th. That is about 7.90 times 10 to the 5th meters per second squared. Let me check that. Yep. And last part. If the neutron star rotates faster, do the answers increase, decrease, or remain the same? So if it rotates faster, that's going to increase this, right? Because that means this will be smaller. The r won't change. If this time period is smaller, that's going to make this bigger. And of course, if that's bigger, that's going to make this bigger. So they will be bigger. They will increase. Last one. At time 2 seconds, the acceleration of a particle in counterclockwise circular motion. Remember, counterclockwise is what we think of as positive direction, usually. Its acceleration is 6i4j. So 6i4j. So that's kind of like this direction. This is 6 and 4. Right? And what is this? This is its acceleration vector, I think. Yes. Right? Now, if it's going in, if you imagine this has to be pointing toward the center of the circle. So we actually know quite a bit about this motion now just based on this, because if this is pointing toward the center of the circle, then the instantaneous direction of travel has to be either this way or this way, if this is pointing toward the center. If this is pointing toward the center, it's like along a radius, and the velocity would be tangent to the path of the circle, so it's got to be either going this way or this way. And I think that we know if it's going in counterclockwise motion, and the center's up here somewhere, it's got to be this one. So the velocity is that direction. And also I can find the magnitude of this because I know about the Pythagorean theorem. My geometry teacher told me about it. 7.2. All right, what do they want to know? It moves at a constant speed of time 5 seconds. The particle's acceleration is 4 negative 6. 4i negative 6j. So what does that look like? 4i negative 6j. All right, so I think it's time to play a little game of pin the tail on the donkey. And by pin the tail on the donkey, what I really mean is pin the centripetal acceleration vector onto the uniform circular motion problem. It's a fun game. Play at kids' birthday parties and stuff. So what we know from this is that I'm going to just sketch this circle here. I've got something that's moving in this. Oops, that's not possible. Just kidding, this is going the wrong way. It's going this way. And I know that here, this is at time 2, and that's pointing toward the center. Now notice here that if this is 6, 4, and this is 4, -6, these are perpendicular to each other, right? That's that you change the x and the y and change the sign of one of them. So it's going down like this, so that must be here. That has to be where we are, and that's at time 5. And it's going this way. So what we need to do here is figure out what the period is. So 3 seconds go by from here to here. So this one, I think it's probably pretty easy to figure out that if it's going 3/4 of the way around, since this is a 90-degree angle here, if this is 3/4 of the way around in 3 seconds, then the period must be 4 seconds. It's possible to set up a proportion if you like to figure that out, but that one's pretty intuitive, I think, once you realize where these are. Okay, that was the missing piece of information that we needed. I think we're probably good now to find whatever we need to find. What is the radius of the path taken by the particle if time 2 to time 1? Okay, so they also told us that time 2 minus time 1 is less than 1 period, because of course it could be going really, really fast and be here at time 2 and zoom around many, many times and then end up here at time 5. What they're telling us is that that's less than 1 full period. So what we did there is correct. So what do we need here? Let's see, what can we do? We might have to set up a little system here, because we were looking for, what is the radius? That's what we were looking for. No multiple parts here. So these are the two things I know. I know this and I know this. And I'm looking at these equations, and I don't have one that has acceleration, period, and the radius of the circle. So I think I'm going to have to try both of these, right, and see what I can do there. So let's see, if I do v is equal to 2 pi r over 4, and then I also have here the magnitude of the centripetal acceleration, 7.2, is equal to v squared over r. Right? So I think if I substitute this here, then I think we're going to be in business. And if there's some easier way to do this that you spotted, then that's great. And this is what presented itself to my math, physics consciousness. I'm saying that because I'm having a weird feeling that there might be an easier way to do this, but this will work just fine. So let's see, if I substitute that, then I get this equation. I'm trying to conserve space here and finish on this same piece of paper. 7.2 is equal to v squared. That's 2 pi r squared over 4 squared all over r, which I'm just going to move that off to the side to make it look a little bit nicer, in my opinion. So let's see what we got now. So 7.2 is equal to let's see, one of the r's, r squared and r, I'm just going to have an r there, and then when I do this math I have 2 pi, that whole thing squared over 16. And you cannot, just in case you are one of these people who does this and you think your calculator knows what you mean there, really got to break that habit. If you want the 2 to get squared also, you have to do this, not optional. So I think that needs to get divided by 16. Oops, syntax error. So that is 2.47, and then so 7.2 divided by that is 2.92. And that's all. That's all I got for you.